It's sometimes nice, especially in differential equations, to have polynomials that are orthogonal to each other under some choice of inner product. In 5.7, which is a book, which is a section we are not going to cover in this course, we don't really have time for it. The book actually covers these so-called orthogonal polynomials. So we won't cover them, but I do want to talk about one of the simplest collections. So this is all from, if you want to actually look it up yourself, and I kind of encourage you to actually look at it. So this is from page 294, and this talks about what we call the Legendre polynomials, or Legendre polynomials. Sorry, I don't really speak French, so sorry if I butcher any names here. But so these are polynomials in, well, technically they're polynomials over the entire real line, but specifically we're looking at continuous functions from -1 to 1 with the inner product. The inner product of f and g is the integral from -1 to 1 of the product of f and g. And we want to find polynomials that are orthogonal under this inner product and are of unit length under that inner product. But we do want to, we want an extra condition on this. We want to basically start with the vectors or functions 1x, x squared, x cubed, x fourth, and so on. Essentially, we want the first Legendre polynomial to only be a constant. The second one to only be linear, that it only has powers up to x1. And then the third one is going to be quadratic. It's only going to have up to x squared, and so on and so forth. Just to essentially mean that we don't have to use too many of them for whatever application we're going to be using. Only up to whatever degree that we're working with. Also, we'll probably number them we'll say that the 0th one is the one that has degree 0. The first one is the one that has degree 1. Just to actually make it agree with the actual degree of the polynomial. So, what we're going to do is we're going to use Gram-Schmidt on these vectors. These are a basis for polynomials, not the entire c -1 to 1, but for polynomials we can always use our powers as a basis. And so we're just going to kind of start with 1 and work our way up. And we won't go for too far, but we'll at least get some of them. Another thing I'm going to mention here is because we're working from -1 to 1, that means if we're looking at x to the n, and n is an odd number, because that means that we're dealing with an odd function, we're always going to get 0. Or specifically, this works for x, x cubed, x to the 5th, and so on. We're going to essentially abuse that fact to make things go a little quicker, so we don't have to go through all the as many steps. So, where do we start? Well, we're trying to use Gram-Schmidt. So we're going to start with 1, and we're going to turn it into a unit vector. Keep in mind, 1 is not unit under this inner product. What is the norm of 1? Maybe I'll make that look like that kind of a 1. Well, to compute the norm, we have to use this inner product. I'm going to go ahead and square it, because what does that mean? We're taking the inner product of 1 with itself. Normally, if we were working in Rn, we just go ahead and take a square root on the other side, but here, this inner product is actually an integral, so I don't want to take a square root of an integral. Let's just look at the square, and then we'll turn that into our norm later on. So, take 1 times 1 as our integrand. We're integrating 1 from -1 to 1. And that instead of, it doesn't turn into 1, it turns into 2. Because we actually have we're covering a length of 2 as our interval. So that means that the norm of 1 is actually square root of 2. Well, I'm also going to take the norm of x, and I'll show you why in a moment. So what we're doing is taking the norm. Remember, we're taking x times x, so we're integrating x squared. When we do that, we get a 1/3 x cubed from -1 to 1, and that gives us a 2/3. So that means that the norm of x is square root of 2 over 3. Now, why am I taking the norm of x? Well, it turns out that if I look at the inner product of 1 and x, so I'm taking 1 times x as my integrand, and notice here we just have an x to the first power, or in other words, we get 0. So 1 and x were already orthogonal to each other. That's not always going to happen when you're doing these Gram-Schmidt problems, but it does happen here. So we didn't actually need to actually make these two orthogonal. We just need to make 1 and x into unit vectors. That was our first step. So you can say our u0, our first basis vector, our first unit vector, we're going to take 1 and we're going to divide it by square root 2. So literally just 1 over square root 2. Our u1, we're going to take x, that's our vector, and we're going to divide it by the square root of 2 over 3. Or in other words, we'll multiply x by the square root of 3 over 2. These are our first of these polynomials that we'll look at. Now we need to move on to x squared. How do we deal with x squared? Well, we need to look at a projection of x squared onto the vectors we've already gotten. So we need the inner product of u1 and u0 with x squared. We'll go ahead and we'll use the formulas from before. So we'll take integral from -1 to 1 of u0, but that's 1 over square root 2, times x squared. We can pull out the 1 over square root 2, integral of x squared. We actually found that a little bit ago. That was 2 over 3. And actually, we can go ahead and turn this into a square root 2 over 3 if we want to rationalize. Do the same thing with u1 x squared. So u1 was square root of 3 over 2 x, but we're multiplying by x squared. And this one is very nice, because x times x squared is x cubed, and the integral of x cubed from -1 to 1 is 0. So actually, we only have to worry about one of these. So what is our, we're taking x squared minus our, you can say it's p, I guess we'll call it p1. It's the you could say it's a projection onto the first degree polynomials. This will be x squared minus the inner product of u0 with x squared times u0. And then technically it's the inner product of u1 with x squared times u1, though that's 0, so that we don't really need that as much. So we have x squared minus this inner product of square root 2 over 3 times u0, but u0 was 1 over square root 2. So ultimately we get x squared minus 1/3. Of course, that's not a unit vector. We have to go a little bit further. We need to take its norm. Its norm squared, just so we don't have to deal with square roots right now, will be the inner product, or it will be the integral from -1 to 1 of x squared minus p1 squared, because we're multiplying it by we're taking the inner product of it with itself, so we have to multiply that function by itself in the integral. So we're going to take x squared minus 1/3. we're going to square it and integrate that. And of course, that's some work. You have to expand this out, you then integrate it, and ultimately you end up with 8 over 45. So I'll leave that to you to actually find that. But that does mean that our norm, x squared minus p1 norm, is going to be the square root of that. So square root of 8 over 45. And in fact, we can simplify this. You can go ahead and actually, I'm going to leave the 5. I'm going to leave the 8 inside, but I am going to pull out a 9 from the 45. That'll give me, when I pull it out of the square root, it's going to change the 9 to a 3, and then I'll have a square root of 8 over 5. And the reason why I wanted to pull out that 3, that 1/3, is because it'll actually change when we divide by it, basically multiply by 3, it's going to change this 1/3 into a 1. So my u2 is going to be x squared minus p1 over the norm. We end up with essentially 3 times this, so we'll have a 3x squared minus 1. But then we'll have to multiply by, well, square root of this reciprocal. So we'll have a square root of 5 over 8. And that is our second, our second degree basis vector. It's a unit vector that is orthogonal to both 1 and x. All right, moving on to x cubed. We want to find what is u3. So we're going to have to take x cubed inner product with u0, with u1, and with u2. We have 3 basis vectors already. We need to take the inner product with all of them. So again, all these are integrals. We're going to put in our basis vectors. And then, what was this? Square root of 5 over 8 times 3x squared minus 1. So those are all the u0, u1, u2, and they're all going to be multiplied by an x cubed. All right, so what do we do? Well, first thing, we notice here that x cubed is an odd function. On this interval, just gives us 0. In fact, we have an odd function here, and everything inside here is even. So, if we distribute that, we have an x to the 5th and an x cubed. Both of those are odd powers, so those all give us 0. The only one that gives us something that's not 0 is this one here. And here we're dealing with the integral of x to the 4th power. And when we do that, well, we're going to get a square root of 6 over 5. Technically, there is some simplification there. I'm not going to go through it. I'm just for sake of time, I'm just going to skip to that. So when we take x cubed minus p2, so we're taking that projection p2 of x cubed onto the span of onto the subspace of all quadratics. We have x cubed minus the inner product of x cubed with u0 times u0 minus the inner product of x cubed with u1 times u1 minus the inner product of x cubed with u2 times u2. Of course, 2 of those turn out to be zeros, but that's okay. Then we have this thing, That inner product is square root of 6 over 5. But then u1 is square root of 3 over 2 times x. And that's going to simplify to x cubed minus 3/5 x. Of course, we need to turn it into a unit vector. Sorry, that should be x cubed minus p2. The norm of this thing, or at least the norm of it squared, because we have to take an integral. We're going to take this vector, and we're going to square it, and then integrate that. Again, I'm going to jump straight to the answer. It's going to be an 8 over 175. So we get to divide we get to get u3, to get our next basis vector. We're going to divide these. X cubed minus p2 over that norm. Of course, the norm here is not 8 over square root 75. It's not 8 over 175. We actually do need to square root this. Of course, you can probably easily see that 175 is divisible by 25. That will actually become unuseful because of the 5 that we have here. I'm going to pull out the 25, and that'll give me a 1/5. But I'm going to go ahead and leave the 8 inside, and the remaining 7 from the 175 in there as well. So you have 1/5 times the square root of 8 over 5. Then when we divide by this, we end up multiplying this result by 5. You can kind of see why I did that. It's for the similar reason as we did before. But then we still have the square root of 7 over 8 out in front. So you have 5x cubed minus 3x. That is our u3. We're going to go one more step. So we're going to look at x to the 4th, and we're going to take its inner product with all the ones we have from before. u0, u1, u2, and now u3. All these inner products are integrals. We're going to put in our u's, so u0 is 1 over square root 2. Then we have square root of 3 over 2. We have square root of, this was 5 over 8 times 3x squared minus 1. And then this was a square root of 7 over 8 times 5x cubed minus 3x. And all these are then going to be multiplied, or sorry, this one had an x in it. These are all going to be multiplied by x to the 4th. And we get to work out what all these integrals are. So first things first, x to the 4th, that does give us something. We can integrate that, and we'll end up with the square root of 2 over 5. Here I rationalized it because we ended up with a 2 on top. Here we have x times x to the 4th. That's x to the 5th. That's an odd function, so we get a 0. For this one, this is the fun one. We do get a lot of stuff. But the square root of square root of 5 over 8, that will stay as it is, and everything else will turn into a 16 over 35. 35 comes from the fact that we end up with x to the 6th and x to the 4th, and when you do the integration, you end up having a 7 and a 5 as your denominators, and those combine to make the 35 that you see here. Finally, here, when we distribute the x to the 4th, we have an x to the 7th and an x to the 5th. Those are both odd, so nothing actually survives here. We get a 0 in this case. So x to the 4th minus p3. And maybe I'm not going to write all this one out, but we do have x to the 4th. We have the inner product of x to the fourth with u0 times u0. The u1 term goes away, so I'm not going to bother writing that one. But we do have the u2 term, and then the u3 term goes away. So this will be x to the fourth minus square root of 2 over 5, but then u0 is 1 over square root of 2. That will simplify nicely. And then we have a square root of 5 over 8 times 16 over 35, but then that's times u2, which is square root of 5 over 8 times 3x squared minus 1. That all simplifies down to x to the fourth minus 6 over 7x squared plus 3 over 35. I get a nice fourth power here. We do need to divide by its norm. And I'm going to kind of, well, actually, let's go ahead. I'll write out the integral. But again, I'm not going to work this thing out. It is kind of a tedious one to do, because we're going to have to take this entire 3-term polynomial, square it, expand that out, which results in quite a few terms, and we get a fun result of 128 over 11,025. There we go. When we divide these, we get our u4. And again, there's some simplification. We can actually we can pull out any fractions. That shouldn't be squared. We can actually get rid of the 35 that's on the bottom, and things actually simplify very nicely. We end up getting a 3 over 8 square root 2. That's a 2. And then 35x to the fourth minus 30x squared plus 3. So not as bad as you might have expected it to be. A much simpler result. So these are not actually the Legendre polynomials. This is a weird case where instead of insisting on them being unit vectors, sometimes it's actually preferable to use another condition. In this case, our Legendre polynomials are going to be polynomials p sub n of x, so n meaning the degree of the polynomial, where p sub n of 1, if we plug in the number 1, we get 1 out. The u's that we got here are unit vectors, and that was pretty important for doing the Gram-Schmidt process. Without turning them into unit vectors, we'd have to modify the process pretty heavily to compensate for that, or the process will just completely break. So we made them unit vectors for that reason, but people like to use this other condition to make it easier to do the computations, and that will actually deal with all the square roots that we've been dealing with. So really we're looking for scalars times these polynomials that will satisfy this condition. So let's think of something that we can multiply u0 by to get a p0, a degree 1 polynomial, or sorry, degree 0 polynomial that has its value at 1 being just 1. Well, that one's pretty easy. It's just 1. We go back to the original 1 that we started with. So one thing you could do here is you could plug 1 in there, see what you get, and then divide by that number, which would just get rid of the 1 over square root 2 that we have here. Similar thing happens with p1. What's the polynomial of degree 1 that has, well, something times, a scalar multiple of this thing, of this u1 that we have here, that does satisfy this condition of p1 of 1 equals 1. Well, this is going to be x. Obviously x is a multiple of this, and if we plug 1 into here, we get 1 out. So kind of made it a little bit more complicated for our first two vectors doing that, but we needed that in order to derive the formula for for u2. Because now, to get p2, it's not so obvious. It's not going to be x squared, even though x squared would satisfy this condition, because it would not be orthogonal to these up here. We want orthogonal polynomials that satisfy this condition. And doing the Gram-Schmidt, it was the process that ensured that we got orthogonal ones. So what's something we could actually multiply this one by to get a polynomial that satisfies our extra condition? Well, we just need to ask, what happens if we plug in 1? If we plug in 1, we have this square root still, times 3 minus 1. So what we get in there is a 2. We need to divide this by 2 times the square root. Of course, that will just get rid of the square root. We're dividing that square root away, but we did have to divide by 2 still. So we have a 1/2 times 3x squared minus 1. This is orthogonal to 1 and x, and it's set in, if you plug in 1, you get 1. That's what we wanted. Do the same thing with p3. We plug in 1 here, we get 5 minus 3 inside here, so at 2. So we need to divide this by 2 times the square root. Of course, that cancels out the square root, but again, we have to divide by that 2. So again, we have a cubic polynomial, where if we plug in 1, we get 1, and it's orthogonal to the 3 that we had before. In fact, this is specifically, it's orthogonal to every quadratic polynomial. Finally, p4. We take this thing, we plug in 1, we get 35 minus 30 plus 3. 35 minus 30 is 5. We add 3 to that to get 8. So we have an 8 in here, and we have this fraction outside. When we actually divide by that value that we get, we cancel on that, but we're left with the 8 that we got here. So we'll get a 1/8 times that polynomial of 35x to the 4th minus 30x squared plus 3. And again, the important thing is that we have a degree 4 polynomial that is orthogonal to these up here. In fact, it's orthogonal to any cubic, and it satisfies the condition of p4 of 1 equals 1. All right. And we could keep going with that. We could find a u5, a u6, and we can turn those into a p5 and a p6. But I will note here that since these have been studied a whole bunch, there is a faster way of deriving them that the book actually goes through a proof of. It actually derives what we call a recurrence relation, where once you have some of them, you can just plug them into a formula and kind of crank out the next one. But at the heart of that theorem that they prove is still that Gram-Schmidt process. It's just that, well, people have developed a way to do it quicker in this particular kind of circumstance. And the book kind of goes through that not only for these Legendre polynomials, but also for other polynomials that are under a different inner product. So if you use a different inner product, you can derive completely different polynomials. And depending on the situation that you're working with, maybe something else might work a little bit nicer. So these are very nice if you're doing anything with approximating functions on the interval from -1 to 1. Kind of having to do with projections into the space of all polynomials. Won't get too into that here, but that's kind of why these come up, is a way to approximate functions. Alright, so I'm going to stop there. Sorry, this was kind of a long example, but I felt it was an interesting thing to look at, an example that was not in Rn, but still used the Gram-Schmidt process. So I'll see you in the next video where we'll talk about the QR factorization of polynomials. And this is another application of this idea. So, see you then.